So this is all nice and good. We've seen lots of drawings, some little microscope photos and stuff, but what about in the field? This is where it kind of matters the most. You're out surveying, you're out studying an area, and you find joints. What do you do? Well, the first thing you have to do is answer the question, why is there jointing? Was it cooling of a igneous rock like Devil's Tower or Giant's Causeway? Is it because of a stress field? Is it because of a nearby fault? Or, what caused the jointing? This will help you determine how to proceed in your study. So this is the important first step. Determine this if you can. If you can't, then you need some more information until you can determine that. And then you can move on. Once you've determined that, if you look in your book, pages 149 and 150, it covers this. You want to look at, okay, is your jointing systematic or non-systematic? Are they parallel or not parallel, and are they irregular? If you have more than one joint set, what are the orientations? Are they orthogonal? Are they at some angle? Do you have the J joints or the sigmoidal joints or the conjugate joints where they're just at different angles but all going straight through? What is the nature of the cross-cutting? Again, J, sigmoidal, or conjugate. What is the surface morphology? Do you see the hackle zone? Do you not see a hackle zone? What can you see at the surface? What are the dimensions? Are these 2-inch joints? Are they hundreds of feet long? How big are they? The joints at Devil's Tower are significantly different than the joints that you might see in a boulder. First of all, the boulder can't have a joint as big as Devil's Tower because it's not as big as Devil's Tower. But it tells you something about the stresses that were present affecting the boulder when it wasn't just sitting there in the open ground. What is the spacing and joint density in the outcrop? This can tell you something about how long it was under those stresses. If you know, for example, that the rock is, dolomite, and the joint spacing doesn't seem appropriate in your outcrop for how tightly spaced they can end up in dolomite, this tells you, hey, you know what? This thing got exposed before it had time for all the joints to form. Tells you something, it was exposed more recently. On the other hand, if the joint spacing is very regular and as tight as you would expect based on experience for that thickness, then this thing was buried for a long time, plenty of time for all the joints to form. How is the distribution of joints affected by lithology? Are all of the layers in your outcrop or your cliff face at maximum joint density? That can, again, help you figure out how long and stress fields and so forth. Are the joints connected to each other or are they isolated? This can tell you about changing stress fields. And how are the joints related to other structures and fabrics? So, if you've got linear features in your rock and the joints are lined up with them, or cross-cutting, that tells you something about the stresses, the stress directions, changes in the stress directions, timing of the stress direction changes, and so forth. Then, if you're going to collect the information to report on it, there's two different ways to collect numerical and visual data on joints. There's the inventory method and the selection method. The inventory method is where you define a region. So out of this whole outcrop, you could say, okay, I'm going to draw a line from here to here, this little dotted line at the top of the outcrop, and every joint that crosses that line, I'm going to count and describe. So I'm going to, give the angle, I'm going to give the length, I'm going to give if it's, curved or not, if there's a hackle zone, all different things that you're describing about each joint crossing it, as well as counting how many joints cross it. Or you could say, okay, this circle, or it could be a box, but this area on the surface, instead of a line, it's an area. I'm going to count and describe all the joints in this area. It could be small like that circle. The area could be this face of the outcrop. Better than doing a whole mountainside, if you're doing one outcrop. But again, it's a specific area, so you're limiting yourself to that area. And then you want to measure them all, describe them, and importantly, determine the dominant joint orientations, whether they're actually master faults, or master joints, or they're just the largest, most dominant joints as far as quantity. You want to determine that. The selection method is, you look at the outcrop, for the outcrop as a whole, determine the dominant joint set or sets, then measure a few. In this case, the dominant joint set are these vertical ones. And so then you could walk over and say, okay, I'm going to measure and describe 3 of these vertical joints. That's a selection. And this allows you to identify fracture joint systems by looking at the set, and this can tell you, since you've determined that they're the dominant joint set, something about the stress field. Now, ways of representing it. This is if you're doing the inventory method, whether it's small scale like this or large scale like a county or a state, looking at larger joints if you're looking at a larger area. For example, here, looking at a large section of New York State. So there's Buffalo and Rochester and Syracuse, so you can see this is covering hundreds of miles. Each of those lines is representing a large-scale joint. Now you could do the same kind of thing for a single outcrop. So in that case, instead of the dotted line being the state border, the dotted line around it could be the shape of the outcrop. And then each of the lines is a different joint in your outcrop. So this can be done to different scales. Or in the top right here, you can see a bar graph. And so up the side in the vertical direction is how many joints are at some given angle, which is your x-axis. So you can see this is in, looks like 20 degrees, so 0 to 20 from a orientation that you determine, such as 0 being parallel to the ground. And, it looks like, I don't know what the vertical scale is on this, but supposing each tick was 10, there were 5 that were parallel to the ground. And then the 20 to 40, 40 to 60, 60 to 80. Actually, I guess they weren't. Maybe they were 15-degree columns. The point is that you should have better labeling than this. This is a horribly labeled bar chart or bar graph. So if you're going to use a bar graph method, make it obvious. Don't do it like this one. Or you can use a rose plot. This is very common for joints and also for faults. Engineers probably especially are familiar with these. This can give you a big indication of stress fields. So you have your 360 degrees as going around the circle, north is identified, and then you measure what angle each of the joints are relative to north, and you plot them. Now, because a joint is a linear feature, if, for example, this looks like it's about 25 degrees east of north, and supposing that bar there represents 100 joints, exactly opposite of it at 205 degrees is an equal number. That's the same set of joints. That's the same, I think, I don't know, 200 joints. I don't remember what number I said. And then this one that's kind of trending northwest and southeast, again, equal length because it's the actual same joints being counted. But the thickness and the length here is telling you how many are in that approximate orientation. And so this tells you about your stress field. This tells you where all the fractures are, which tells you what stresses caused all those fractures. Now, brittle faulting. Stepping away from jointing slightly here. So we've got faulting, so there is movement. This means that sigma 1 and sigma 3 have to be different, and the fault surface, the fault plane, is not parallel to sigma 1, 2, or 3. It has to be at some angle to get movement. We can get brittle faulting, as we covered last chapter, when we have reactivation of a formerly fractured rock, so it filled in with vein, some mineral weaker than the rock, new stresses reactivate the fracture, or the solid rock, lots of compression, and then those Griffith cracks start growing, and you eventually get a through growing crack, and then movement along that crack, so it's faulting. So those are the two ways we get brittle faults.